G'day viewers. In this segment we'll talk about codes which can be used to correct errors in messages received across links. So the context for this segment is the same as the previous two, which is that we know that messages can be received with errors caused by noise in the physical layer. What we would like to do in this segment is devise code so that we can look at the structure of the message, the bits we receive, and from those bits work out not only that an error has occurred, but guess what the message was which was actually sent. So this goes a step beyond codes for simply detecting that an error has occurred. And we will go through the example of Hamming codes. They're one of the simplest, realistic error correcting codes. And then I'll mention other codes which are used in practice. Finally, we'll talk about why you might use detection rather than correction. Since it seems as if you could come up with codes for error correction, then you would want to use them rather than detection because they're stronger. But it's not quite that simple. Okay, well, to get the ball rolling here, let me remind you why error correction is hard. Now, if we had reliable check bits that you could send to go with the data bits, everything would be much easier. You could send that reliable information and use them to describe the structure of the message and narrow down where the error was in the data. But of course there can be problems in all of the check bits. In fact, the error could be in the check bits as well as the data bits. The data might even be correct. That would be all we would care about. If the error was in the check bits, that would maybe throw us off and we would think there was an error even though we actually wouldn't necessarily care about it. Going a little further, just suppose for the moment that we could construct a Hamming code with a distance of 3. That means that we would need at least 3 single-bit errors to transform a valid code word to any other valid code word. If we then have a single-bit error, that will be closest to a single unique valid code word. So if we can assume, and here's one of the key assumptions, if we can assume that the errors we will see in practice will only be either 0 or 1 bit, then we can correct errors by mapping whatever bits we receive to the closest valid code word. This argument also generalizes to work for correcting D errors if you have a Hamming distance of 2D plus 1. Here's a diagram that helps us visualize this intuition. You can see here in this code, the pink circles represent a valid code word, so the data bits and the check bits match. Whereas the grey circles here, they represent an error code word where you've got a bunch of bits in, but the data and the check bits don't match. This code has a Hamming distance of 3 because we need to go at least 3 hops, which is changing 3 bits to get from any valid code word to any other one. Here's another one. Now let's look around A. This circle, this is the code words which are within a single bit error of A. What we will do for correction is when we get in a code word such as this one here, we will say this is closest to A, so therefore I'm going to correct that by saying A would be sent. You can see that must be the case if we got either 0 or 1 error, because there's no other way that we could have got from a valid code word to be so close to A. This slide just cleans it up a little bit so you can see it a little more clearly. Okay, so Hamming codes give us a way of constructing this code with a Hamming distance of 3 and also an easy decoding method which will allow us to do the correction and move to the closest valid code word. In a Hamming code, there are parameterized families, so if you pick a k for a number of check bits, then you can work out n, how many data bits go with that using the expression 2 to the k minus 1. If I have k for 3, for example, then I will end up being able to send up to 4 data bits. The way a Hamming code is constructed is you take all of these bits in the code word together and you lay them out, putting check bits in any position p that is a power of 2, starting your numbering from 1. The check bit in the position p is then a parity sum over all of the positions which have a p term in their binary values when you write them out. Okay, that's all a big mouthful. Let's work through an example to see how it goes. Okay, now here we have some data. The data is 0, 1, 0, 0. We're going to use 3 check bits, so we have 7 bits altogether. They're shown at the bottom here. Let me just write in the parity bits or check bits, and the data bits. Parity will be in positions that are powers of 2. So that's 1, 2, and 4. These are going to be the check bits. The data then will go elsewhere. So if I write the data in left to right, I've got a 0, 1, 0, 1. Now let's compute some of these parity sums. Check position 1 covers the check bit in position 1 is going to cover all other positions which have a 1 in their binary expression. That's going to be 1, 3, 5, and 7. That's P1. We can ignore the 1 itself because there's nothing in it yet. We're going to add it the 3, the 5, and the 7. 0 plus 1 is equal to 0. We'll put a 0 in here. Check bit 2 is going to cover positions with 2 bit turned on in the binary expression. That'll be 2 and 3 and 6 and 7. The parity sum here, 2 and 3 is 0, 6 and 7 is 0, 1, that's equal to 1. So we'll put a 1 here. Parity bit 3 is going to cover positions where there is a 4 in the binary expression. So that is 4, 5, 6, and 7. So if we add those together, 1 and 0 and 1, we get a 1. So I'll write a 1 here. This then is how we constructed a code word for that particular data in the Hamming code with 4 data bits and 3 check bits. And that will then get sent out the wire. Okay, here's a cleaned up version of that. And I think we have our parity sums right. Do we or not? 1, 0, 1. Oops, no, I didn't. I flipped back. 1 plus 0 plus 1, that is a 0. So parity bit 3 in the 4th position here should have been 0. Okay, now we have that right. Moving ahead, the Hamming code gives us a way to decode these codes. What we do is we proceed by recomputing all of these check bits using the same parity sums, now including the check bit parity value itself, because there's a value in there. We then take those check bits and arrange them as a binary number and look at the value. This value is called the syndrome. This value will tell us the position of an error. If it's 0, there's no error. If it's another number like 3, for instance, then the bit in position 3 is wrong and we should flip it to correct the value. Wow, it's pretty cool that this works out. This was all worked out by Richard Hamming, and you can read about it in his paper that I mentioned in a previous segment. So we better try and work through an example. Okay, here is the code word just that we had from before with all of the parity sums computed. Let's recompute the parity bits. Parity bit 1, we're going to add positions 1, 3, 5, 7, and that's equal to 0. Parity bit 2, we're going to add 2 and 3, and 6 and 7, that's a 0. Parity bit 4, we're going to add positions 4, 5, 6, and 7, that's a 0, plus a 1, plus a 0, plus a 1, and guess what? That's a 0. Our syndrome is 0, 0, 0, so there's no error. Yay? Then our data is what we get if we take everything but the check bits. We see it is 0 in position 3, 1 in position 5, 0, 1 in 6 and 7. Here's a cleaned up version. On the other hand, we might actually have had an error during transmission and we want to correct it. That's the whole point. So let's check to see that this method actually works. Parity sum 1. We add up positions 1, it's a 0, 3, 5, and 7. We get a 0. Parity bit 2. We add up positions 2 and 3, and 6 and 7. That is a 1. Parity bit 4. We add up positions 4, 5, 6, 7. That is also a 1. Okay, what's our syndrome then? The lowest order digit is parity bit 1 in position binary at the least significant bit, that's a 0. Ahead of that we have a 1 and a 1, or 6, the binary representation of 6. This means that there is an error in position 6, which we can see is right. So we're going to flip that. The data that we get then is a 0, a 0, a 1, sorry, a 0 and a 1, a 0 and a 1. That's what, and that's what the real data should be. Yes, and we can see here that it's correct after we've flipped the bits. Now, the bad news here is that the error codes for correction which are used in practice are generally much more complicated than the Hamming codes. Hamming codes are useful, but they're fairly simple. Some codes which are widely used in practice are convolutional codes. They tend to take a stream of data and they output a mix of bits at all positions. This mixing process makes the output bits less fragile. They're decoded with what's called a Viterbi algorithm, which has the advantage that it can use the confidence information from the bit values from the physical layer. So we can know if some signal was really high and it really looked like a 1, or if it was close to 50-50 and maybe it was a 1. This turns out to be useful. There's another kind of error code which is becoming widely used in practice, and that is the low-density parity check code. Low-density parity check codes are based on the mathematics of sparse matrices, and they're decoded iteratively using what's called a belief propagation algorithm. This is the same algorithm which is used in machine learning, also comes up in communications. They're state-of-the-art codes today, and they're increasingly being widely used. An interesting side note is they were invented by Robert Gallagher, one of the sort of pioneers of network more on the theory side, as part of his PhD thesis in 1963. And then they were promptly forgotten for more than 30 years, put aside until they were computationally more viable, because they do involve a fair amount of computation. And now those codes are all of the rage. I can also talk briefly about error detection versus correction. Let's consider a hypothetical example. What would it be better to use, error detection or error correction, for a particular example? It's going to turn out that which one we will want to use is going to depend on the kinds of errors, the patterns of errors we're going to correct. But suppose you have messages which are 1,000 bits long, and you have an average bit error rate, or BER, of 1 in 10,000. That means on average, 1 bit will be an error out of 10,000 bits over a long-term average. What should we use, detection or correction? What do you think? How would we even go about working this out? Really, we would like to use the scheme which has least overhead. That will be our measure of goodness. But it turns out that we can't work it out yet. We actually need to know more about what kinds of errors would actually occur. So I'm going to posit two different models. The first model for our errors is the random. 1 in 1,000 bits are errored at random. Well, 1 in 10,000 bits are errored at random. This means that any message is likely to have 0 or at most 1 errors. Most of them have 0. Now, to do error correction, to handle about 1,000 bits, if you go through some of the Hamming expressions from before, you'll find that you need about 10 check bits to be able to correct a single error. So the overhead here per message is how we'll work it, would be simply 10 check bits, 10 bits. On the other hand, that's for error correction. On the other hand, suppose we used error detection. In this case, we would need only, let's say, 1 check bit to detect that there's an error, because we could use a simple parity bit if we're going to have 0 or 1 bits wrong. But then, of course, if there was an error, and this will happen maybe 1/10 of the time, if messages are 1,000 bits and we're going to have an error every 10,000 bits or so, then 1/10 of the time we're going to have to retransmit that message, and we'll have to send 1,000 bits to retransmit it. And this is a rough approximation, but this is going to get us close enough. The overhead then will roughly be 1 check bit plus 1,000 bits, 1/10 of the time. That's 100. Just call it 101 check bits. Wow. Well, that's a lot of overhead. So we would be paying a lot of overhead to detect those errors. For the random error case where errors occur, it seems to be better to use error correction. On the other hand, here's a different model. Let's assume that errors come in bursts of 100. Well, in this case, rather than having 1 in every 10 packets likely to contain an error, we're likely to have not 1 in every 10, but 1 in every 1,000 packets have an error, or maybe 2 out of every 1,000 if those 100 bits are spread across 2 packets. So errors are going to be rarer in terms of packets or frames, but when they occur, boy, it's a big error. If we use error correction, you've got to send the correction on every frame just in case it's in error. How many bits would we need? I don't know how many bits you'd need to correct an error that's that large, 100 bursts of 100 bits. Let's just say you need at least 100 bits of error correcting code to be able to correct 100-bit errors, probably a lot more. What about for error detection? Well, we would like to be able to detect something that's gone wrong even when there are 100 bits in error. How many bits to do that will we need? I'm not sure. Maybe something like 32, because then we would have the probability of 1 on 2 to the 32 that something's gone wrong. That's quite small. That's basically 1 on 4 billion of missing an error if there's a nice random error. So 32 might do it there. Plus, of course, if you actually do get an error, you'll need to retransmit it. So we'll need to send 1,000 bits again, but we'll only need to resend these bits 2/1000ths of the time. So we're going to need, our overhead here will be 32 plus 1,000 divided by 2/1000. So 1,000 divided by 1,000 times 2. So that's 2. That's about 34 bits. You can see that the overhead here is mostly error detection code, not the retransmissions. So in fact, for this case, error detection turns out to be better. To summarize that point, error correction is most useful when the errors are expected. It's the normal case. As an interesting aside, they're also useful when there's no time to do a retransmission because you need information delivered quickly. Error detection, on the other hand, is usually more efficient when errors aren't the expected case. So sending along error correcting code information would just send more bits which are wasted. Or when errors are large when they do occur, because in that case you would need an awful lot of error correcting code bits to be able to deal with them. And finally, let me tell you a little bit about error correction in practice. We find that error correction is heavily used in the physical layer, usually with advanced codes like the low density parity check code. That's becoming common. Older convolutional codes are in fact widely used in practice, but LDPC is going to be the code of the future for all sorts of uses, Wi-Fi, digital television, 4th generation cellular, and so forth. And that's because errors are expected, the normal case in the physical layer, and we'd like to throw some machinery at correcting them. On the other hand, error detection is widely used with retransmission techniques above the physical layer, so in the link layer and above, in the transport layer too. This kind of mechanism is really about dealing with residual errors once the physical layer's got a lot of them down. We'll also see much later on perhaps that correction is also used in the application layer. When it's used in this context, it's often called forward error correction. This usage also has a different kind of error model. Usually at the application level, if you're correcting errors, you know when you've lost bits. Maybe you would lose a whole frame and stripe your information across multiple frames and want to correct it. This error model is called an erasure model. But previously we didn't know if there was an error, which bits they were in. Now, here you know that there's an error in a bit and you don't know what it is. This is actually very close to the setup that's used for codes that you might have heard of, like Reed-Solomon codes, which are used widely in CDs, DVDs, and so forth. So that if you were to lose some information on the disk due to a scratch or something, you could use an error correcting code to work out what the information was. So that's error correction. Now you know something about how to detect and correct errors in messages that are sent across the network.